I'm Mark Anderson, and I'm an engineering consultant with Staties Incorporated. My background is chemical engineering. I'm also a certified quality engineer and master in business administration. So I've been through a long career arc, starting off in R&D for specialty chemical, working in management areas, marketing, purchasing, general management, and running Staties for many years. And now I've come at the other end of my career and back to the engineering. And so my role now is strictly to help people that are developing an interest in our software to foster that and foster their interest in DOE and do a lot of training, consulting, writing, and things like that. So I'm very happy to talk to you about some of my ideas on selecting a most useful predictive model using the tools of Staties software. So again, welcome. I appreciate you all staying on mute. Chat would be addressed afterward. I would say, maybe not, because it's just too hard to try to keep track of it since I'm presenting this solo and I don't have somebody monitoring the chat. So I really suggest then that as you develop questions along the way, you jot them down and then email them directly to me afterwards, mark@staties.com. That'll be the best way of communicating with me, you know, how you like the presentation, questions that arise, anything I can do to help you further your cause, that's my mission. This presentation will be posted afterwards to this website, our 3w.staties.com webinars. You can go there and you'll also see a video at some point within a day or two that'll go to the YouTube posting. So one more time then, just please press that raise hand button if you're with me. Okay, there we go. We've got a do weighing in, Chelsea, Mauricio, a few more people, Susan, Tim, etc. Great. Okay, well, we've got a nice little group here today, and this also will be posted, as I say, to YouTube, and it really presents a nice addition to our library. People are really learning a lot about DOE by going to the Staties YouTube channel and picking up on these webinars. Okay, so what's in it for you to attend this webinar or watch it on YouTube? Well, the goal is to achieve I call it statistically solid predictive model. Now, the models may not be perfect, but if they're good enough, then they can be useful and you can press ahead to make a prediction of what's going to happen, do that for multiple responses, and find where the sweet spot is where all your requirements are met. The focus on this webinar is primarily response surface designs or response surface method designs, or RSM, which is a tool for process optimization. However, the tools that I'm presenting and the tips I'm going to provide will work equally well for mixture design where you're trying to optimize a formulation. So what I'm trying to do is provide some tips here on model selection, and in particular what we call algorithmic model reduction, which is a systematic stepwise approach using various criteria to try to get just the simplest model that you can find, or what the statisticians call the most parsimonious model. So what we want to do is avoid overfitting. Of course, we want to be careful not to underfit as well. So we want to get just the right fit that will produce a useful model or map of future performance. And then as I'm going through, I'm going to focus on the key statistics. There's lots of statistics, that's even a hard word to say, that we can look at, but there's just going to be a handful of stats that are really most useful for assessing your model fit. And then we'll talk just a little bit on the top 3 diagnostics of normality. We don't want to overlook that to make sure that we're not violating any assumptions for the fit. And then how to detect outliers with a simple graph. And then potentially advantages that might be gained by transforming your response and then refitting it in that metric. For example, the log transformation is one that's commonly used. So this is going to be kind of an ad hoc, off the cuff presentation I'm going to try to provide for you some of the things I look for when I'm looking at client data. And believe me, I've seen a lot of data come through over the last several decades since Daddy's was started up in 1982, and I predate that as one of the original founders of the company, alongside our founding principal, Pat Whitcomb, even going before 1982. So I've seen a lot of data over the years, and so I've learned to focus on just the key things so I can quickly kind of assess, just like you would go in to your medical doctor for your annual physical and they're going to look at certain things. I would do the same thing with your data. And so I'll try to pass that along to you. So before we start, I just want to say that as we focus on these response surface methods, that we don't want to overlook the idea of using factorial screening and what's called characterization, which are two-level designs as a starting point before we get into the in-depth modeling, because we want to make sure we get the number of factors down to just the vital few. I think for developing a really strong predictive model, it's good to get down to, let's say, no more than 5 factors. And if you can get down to 2 or 3 or 4, that would be good. So once we get down to those vital few factors, then we're ready to apply this empirical approach of response surface methods. These were developed by George Box in 1951 with his collaborator Wilson at Imperial Chemical. And what's cool about the history of this is that Box is the son-in-law of Ronald Fisher, who invented the two-level factorial designs, analysis of variance, the F-test, and all the modern day statistics go back to Box's father-in-law, Ronald Fisher. But what's good about Box is he developed a real practical focus, whereas Fisher was a little bit more academic and worked in the fields of agriculture. As Box got into kind of becoming a happenstance statistician during World War II, and then started applying it to industry, he recognized that a good flexible strategy would be important, and not to get hung up on whether the models are true or not. They're probably wrong. In fact, he was categorical in saying all models are wrong. But the idea is to provide some that are useful in some form or fashion. So it's an empirical approach that is tried and true going back to 1951. Once you get through the screening phase and characterization, and you begin to see that there's a need for response surface methods, then you're ready to go and apply those factors against the process. And in the process RSM, you may have heard there's a design that's called the central composite. This was the invention of George Box. So this would be the type of experiment you might run, a central composite design, or CCD. And this is the design that's also known as Box-Wilson, after George Box and his collaborator Wilson. Now the design that you would run is fairly simple. It's just a factorial design, which is two-level with a center point run a number of times. And then outside of the original range, to develop a higher order polynomial model, what's called a quadratic, we add these axial points or star points that stick out from the square of the factorial design. So that's the design that you could run. You could run a full 3-level design, but if you did that, the number of combinations begin to really explode. And so I don't recommend full 3-level unless you just have 2 factors. And then one other design I'll just mention at this point, because I've been talking to some people about this option. It's called a Box-Benton design. And this design is one that is nice because it just has 3 levels. And so it's a nice alternative, but the central composite design gets more extreme. Some people like that, and it's got more levels, which is maybe advantageous. And it provides some really nice properties in terms of breaking down the design into the core factorial and the star points. That's just a little sidebar, but whatever design you run, you collect the data, you measure the responses, which are the Y's, and then we do a fitting using least square regression, and then we create this polynomial model. And this model is going to be one that predicts the response, which is a Y with a hat over it, as a function of not just the main effects. Let's say we have 2 factors, so we certainly want to be able to estimate those main effects of x1, x2. the two-level design will estimate the interaction effect, but what we're going to try to do with the responsiveness methods is also fit these squared terms, and that's what's going to make life interesting, because with these squared terms that form a quadratic polynomial model, we can fit some really cool surfaces like rising ridges, pure peaks, pure valleys, or even what's called a saddle point that looks kind of like a Pringles potato chip. And this then, using the software, we can map it out with contour graphs in 2D and show some really cool 3D graphs as well. So this is a really, really powerful approach to try to optimize your process, trying to stabilize it so it's most robust to variations in input factors. And like I say, get a sweet spot for multiple responses where everything is met. So this will be the gist of my presentation. We'll be going through this tutorial that is available within the program. And what I'm going to do is actually use States 360, which is a higher level from our core program, which is Design Expert. Now, most of the people I work with, which are industrial R&D, are very fine using Design Expert, which has been around for decades and decades. But more recently, our top-notch staff, Martin Beziner, who's our current president and PhD statistician, and Hank Anderson, my number 2 son, who's the head of the programming, came up with some additional tools that they incorporated into States 360. And the idea of it is that they had a broader vision, hence the number 360, more of a broader vision. And the big thing that's added on to the States 360 is a Python script editor, which really expands the potential. Now, not everybody out there, and probably just a few of you, would ever want to delve into Python scripting. However, just keep that in mind. And so I'll be using States 360, but I'll be demonstrating features of Design Expert. And what I'm going to do is go back to something I'm familiar with as a chemical engineer working in process development and R&D, taking something that the PhD chemists put together, scaling it up through the pilot plant, and then transferring it out to the manufacturing site. And this would be a study, and these are typical parameters I would be looking at to try to scale up: time of reaction, the temperature of reaction, and then the amount of catalysts that went in. For example, I worked on catalytic hydrogenation, trying to clarify vegetable oil for General Mills. And 2 key responses in this case study, which are fairly typical, is conversion. We want to make sure the conversion or the yield is maximized. And then there's usually product attributes. In this case, there's a product attribute called activity that needs to meet a specification with a target of 63 plus or minus 3. Now, we are going to apply the central composite design that Box and Wilson invented. And what's nice about it is that it's very modular, as I mentioned. In this case, and I would oftentimes suggest this, we would run this in 2 blocks. The first block is a 2-level factorial with the center points. So that was a square with the center points like this. And then in the second block, we run these star points, which are on the outside. Now in the second block, we add some more center points, and this will provide a link from one block to the next. So that's basically the structure of the design. So what I'm going to do then is I'm going to go back to, and I'm going to open up the States 360. Now at this point, I'm just going to ask you all, do you see this flash screen that came up that says States 360? And if you see that, then put your hand up. Okay, Verena provides at least the canary in the coal mine, Susan, and some others. So even just one is enough to know that the internet is working. I'm going to make that assumption, but I do appreciate as many of you putting your hand up along the way as you like, because that gives me some nice positive feedback, working at a distance here. All right, so now this case study is provided in the tutorial on responsiveness methods. All right, and in that tutorial, it's got a lot of information. I wrote this many years ago and I've kept it up all the years. But for example, we have this nice picture of 3-factor central composite, which I didn't try to draw with the 3 dimensions, I just did 2-factor. But you can see how it's got the cubical core factorial with the center points. And then we've added in these axial points sticking out from the cube. And that's the structure of the design. Okay, so then we can open up the data. And in the notes, it recaps, where this data file came from and what the purpose of it is. But straight away, we can look at the actual results, and we can see that it's broken into 2 blocks. On day 1 is the factorial core. So you can see there's a random pattern of different factorial points. Center points are scattered about. And we've got the 3 factors going high and low, and somewhere in the middle, and then measuring the conversion activity. So this would be the actual recipe sheet. On the second day, you come back. And what's nice about this is potentially if these days were separated, let's say by a week, you could actually go back and just look at the factorial results. And you might see that maybe we want to make some shifts in the time and temperature and then start over again. So this is a nice flexible approach, but let's say we just keep going on because it's going to take a while to get the results back from analytical. And we just go ahead and run the second block, which include these axial points that are sticking out high and low, below and above, anything we had done before, and with some additional center points. Okay, so now I'll just quickly run through this one more time, how we built up this design using the design expert or States 360, it doesn't matter. And you can see these choices of the central composite, the box Venkin, which is essentially a cube with the points at the centers of the edges. It doesn't push out as far. And some people like that, and it's only got 3 levels. That could have been an option, but they went with the central composite, and this has got the more modular capability of going into 1, 2, or 3 blocks. And so then, it's just a matter of putting the names, the units of measure, the levels that you want, and then we have a helpful readout on how far out those points are going to go, just so you know. We don't want to get too extreme. Sometimes, for example, the catalyst would get so low on this lower star point, which is called minus alpha. That's the quoted distance out from the center. And that might be so low that the reaction would not initiate, so you would have to do something a little bit different. Now, keep in mind is if you're a user of States software, or if you trial the software, you'll get help from me. And if you're a user, you get a more extended group of people, our whole consulting staff available. So if you have questions, if you're trial using or using the software, then we can really provide some good handholding for you. But even if you don't use the software, I'd be happy to entertain questions to the mark@states.com, just because I'm generally trying to promote the use of these techniques. And so I'm always happy to talk to people, even if they don't use our software. Okay, so here's where we put in the names of the blocks. Now this could be a different way of blocking. It could be lot by lot, which is something I did quite a lot as a chemical engineer because I was working with natural raw materials with General Mills, which is a giant food company. So the lots could be blocked. So this could have been lot 1 and lot 2. Another thing very commonly that I ran across is we had multiple reactors. And so we could do reactor 1 versus reactor 2, and I could actually do them side by side. And that would be kind of a neat way to work in parallel and speed up the process. But day by day is a very common way of blocking. That way, if there's some kind of a shift up or down, we remove that variability. Now I'm talking about a lot of different aspects here. So, if it's getting to be a lot of information, start jotting down on a piece of paper some thoughts, and feel free to come back to me later, as I mentioned, with questions after the presentation. Okay, so here's our 2 responses, and there's really no limit on the number, but very typically you'd have one that represents the productivity, which is the yield or conversion, and another response might be the quality of what you're producing, which is meaning the specifications of activity. And so these are kind of 2 common types of responses. Okay, now I'm going to skip by something here. There is a way to check to see if the number of runs that we've created here, which is 18 runs, will be sufficient to fit the surface with the precision that we're aiming for, given the variation in the system. And that uses a technique called fraction of design space. So you could write that down, fraction of design space, or FDS. That would be a topic of a different presentation. You'd probably find it on our YouTube library, how to make sure that the design is sized properly. So I'm just going to skip by that because I can't cover everything all at once. So what I'm going to do then, since our focus is on fitting models, I better get to it. I'm going to go ahead and reopen this file. with the data, and now we're going to start working on the fitting. So let's start off with a conversion. And I'm going to apply no transformation to this, but later when we look at the diagnostics, there's a specialized plot called the Box-Cox plot that might lead us to go back and reanalyze, for example, using a natural log. However, in this case, if I was to look at the summary and look at the response range, here it's not ranging that much. It's going from a minimum of 51 up to a maximum of 97. That's nice to see, that we're getting near 100% conversion. So I'm pretty happy with that. That range is probably more than the normal variation by far, but the ratio of it is not that great that, we would probably be concerned about doing a log transformation, for example. And the same thing applies to the activity. That's not showing a real extreme range. So I'm pretty sure that we'll be able to analyze this as is, but we'll see what happens later on that. Okay, so we start the analysis, and now it's doing the least square fitting. And so then we're going to take a look at what the program produces for the modeling. All right, and so here's what we get. We get this interesting little setup in terms of the fitting. Now remember I said one of the principles of good modeling is called parsimony, or keeping it simple statistically and not overfitting. So at this point we should think about what was the design geared for, and it turns out that when Box put this together, he designed kind of the perfect structure to fit just the quadratic model. And he felt like that was enough. We didn't have to go to third order, which would be a cubic model or anything like that. So keeping in mind that this design was designed to fit a quadratic, let's see what happens. Now, you can set up designs that'll fit higher order models, but you'd have to use what are called computer optimal or optimal custom designs, and you could actually tell the computer, well, I really want to fit a cubic or a quartic, but usually quadratic will suffice. So now what we're going to do is, keeping that in mind, we're going to consider that potentially we don't have to fit all the terms in the quadratic. Maybe less than a quadratic would work. And one of the first things that we have to consider is that perhaps nothing was significant, and our model would just be the mean model, which has two meanings, because mean is not nice, and mean also means just the average. So I always kind of think of that in two ways, because when I'm trying to discover something, I'd be very disappointed if only the average was needed and we didn't need to actually fit any other terms, but that could be a possibility. So what we'll do is we'll regress that out before we start. We'll also filter out the block differences before we start. And now we begin to consider, what if we just put the main effects or linear terms in? Would that be significant? And in this case, it's no if we're using 0.05. 0.1 might be a little bit more relaxed on p-value, but even it's above that. But when we go to the next level, above and beyond the linear, and fit the next layer of terms, that layer of two-factor interaction terms is significant. So we're beginning to improve the model, but then when we go to the quadratic, we see that that's really the most significant. And so what we've done is we've built up from the mean, corrected for the blocks, we've added a layer of linear terms, two-factor interaction terms, and we've ended right back up with the quadratic. And based on everything that the program is seeing at this point, that's what it's suggesting. Now, we might be tempted to say, well, what if we went even further because more terms would be better, right? No, not really, because for one thing, if we go to the cubic layer, the terms become alias because the design doesn't support all those cubic terms. Secondly, that layer is not significant, so we don't have any business going there. So let's settle for quadratic. That's what we thought we would get, and that's what's suggested. Now we're going to test that quadratic for its lack of fit. And obviously we want that p-value for lack of fit to be high. So that's good, it's high. Now, if we were to go back and downgrade the model to two-factor interaction, that p-value would become lower, which is bad. And of course, if we just use linear terms, it would be very significant, well, significant at 0.05. So certainly the quadratic is merited by the lack of fit being insignificant. And then there's a few other stats we can look at And in particular, what I would focus on is not this raw R squared, which continually goes up as you add more terms, and that would cause you to systematically overfit the data, but rather go to the adjusted R squared that penalizes for the number of parameters in the model. And you can see that it degrades when you add those cubic terms. Okay, so that the highest adjusted R squared is the quadratic. That's good. And then an even more rigorous for predictive purposes, which is what we're trying to do with the DOEs, is the predicted R squared. It's based on a predicted residual sum of squares, which is taking each point out in turn, refitting, regenerating the sum of squares differences of actual predicted, and blah, blah, blah. And if you're interested in what PRESS is, you can look on the help system. Oftentimes there's help available under the covers directly, but never mind that. Just look at this predicted R squared as a form of R squared. We want it to get, as close to 1 as we can. And this is very good at 0.7891. And so what you're going to see then is the R squared will always be the highest. It'll drop off a little bit to adjusted R squared, and the most severe R squared, predicted R squared, which I think is the best one, will drop off a little bit further, but this is actually a very good predicted R squared. Anything above 0 really is not unacceptable. Of course, the higher the better. And all of this is summarized in this first table. So here we have a summary of the sequential p-value. We see a summary of the lack of fit p-value, and then the 2 key R squared is adjusted and predicted. Okay, so now we're ready to continue on, and we see that indeed the software has picked the process order quadratic, which is what we designed the model, designed the experiment to fit, and so that's also our design model. And we see the main effect terms, which are time, temperature, catalyst. We see a series of two-factor interaction terms, A, B, A, C, B, C. And then these are the quadratic terms, A squared, B squared, C squared. But are they all significant? Maybe, maybe not. The more terms you have, the more likely you're going to see, lots of insignificant terms. And maybe that would just, be kind of, messy to have all those. So what we do is we go to the ANOVA and we look at the p-values first. And what we see here is that some of the terms, like the term for time, the main effect of time, is quite insignificant. The interactions of AB and, well, I guess AB interaction is insignificant, and then A squared is insignificant. So A, going through this whole thing doesn't seem to have as much of an effect at the time. However, we're going to have to be a little bit careful because possibly there's some higher order terms that are going to require terms under it to provide support. And this is what's called a hierarchical model. So just observing our terms here, I see that AC is very significant. Time does matter, but in the context of the catalyst. But nevertheless, we could go back and manually say, well, let's just eliminate time. Let's eliminate the AB interaction, and let's eliminate the A squared because those had higher p-values, and refit this. Well, this is what I thought would happen. It says the model you have selected is not hierarchical. Would you like to have it corrected? I would say yes, because that's good modeling, and then A has to come back in to support the AC term. All right, so this is one way to pare things back, and the payoff of all this is that you usually see somewhat better predicted R squared in particular. Let's just see the predicted R squared of 0.7326. And originally, so I don't know if I'm not sure I really did any good in this case, but even so, I do like reducing models, if nothing else, because when you look at your model and report that in your publication, you're going to have a more parsimonious model, and it's going to be simpler for your team and for the readers if you're publishing in a peer-reviewed journal, not to be looking at terms that are insignificant and not needed for the model. So I do like having the models reduced. All right, so I'm just going to pause here for a second, and before I show you some tricks with the model reduction algorithmically, just check and see if you're still with me, on the internet. by pressing that raise hand button. Okay, great. So I'm seeing you're still with me. And just while I took a little break here, I noticed there was a question came in from Verena. Is there an option with Design Expert to model blocks as random effects? Excellent, Verena, because yes, that is a good point. In our newer versions of StatEase 360, we've added the ability to model blocks as random effects. Now, this would be, for example, if we're blocking on something like lot or day that we don't really control. If it was two different pieces of equipment or two different suppliers that we're blocking out, that might be different. Those would be more fixed factors rather than random factors. However, and you can go back and see a webinar by Martin Bessener on this, what happens is oftentimes the advantage of using random blocking as a modeling tool is so minor that it's kind of it's outweighed by the complexity of it. But nevertheless, if you're more a high-powered user, such as a master statistician or a really advanced DOE practitioner, StatEase 360 would be good to get because you do have that option. And you can look at it both from the point of view of fixed blocks, which I'm doing here, or random blocks and kind of decide what works for you best in the end. And then Wolfgang is asking, what can you do if you measure on different days and also have different reactors? What blocking structure should I use? Well, what I recommend, and remember that I'm a chemical engineer, I'm not a statistician, but what I recommend is that you do multiple blocking. Okay, so let's say, well, what I would do as a chemie is if I had two reactors, I would say, okay, Joe, I'm going to have you operate reactor 1, and Mary, you're going to operate reactor 2. Now I'm actually blocking then who is doing the reaction and the reactor. But if you think about it, the reactors are also located at different places in the factory. Even if they're side by side, they could have a small little difference because one's got the air conditioning blowing on it and one doesn't. And so there's lots of different things that are happening. So I think you just kind of wave your hands and say, look, I'm just going to block all of that out because all I want to do is focus on how the time temperature catalyst is affecting things. And if there's not that much of a difference, and it's just a shift up and down very slightly between the lot by lot or whatever it is we're blocking, then I'm not going to worry about that because if I've optimized the reaction, it's always going to be the best, whether it's this reactor at this location with this operator, as long as I'm developing fairly consistent, results. In other words, just a shift between them, not a complete change in the model. So you do have to apply some subject matter knowledge. I would be concerned if the difference in blocks is large. I would go back as the engineer and try to figure out, well, what happened? Did Joe not follow the procedure? And so his yields were systematically lower, by an important amount. I would bear down on that. Is there something with this reactor that's kind of degrading versus the other reactor? Was there something odd about this lot of material that came in, or something happened that particular day that's different? So we try to investigate if there's differences in the blocks. So thank you for those questions. They were very good. But I want to get back on focus here because we're talking about modeling and trying to come up with a useful model. So what I'm going to suggest is that you first look at the ANOVA and check out the p-values and try to assess what's going on with the full model. But then once you do that, rather than manually reducing out, which is kind of a pain, you revert back to the original model and then use this auto select. Now I happen to be partial to the criterion of p-values, and using a threshold value of 0.1, which you could modify. This is a p-value above which you're going to remove terms. 0.1 probably isn't a bad idea because there's a lot of things going on during this algorithmic reduction. So we want to be a little bit less rigorous on the p-value than normal. Normally we'd say 0.05, but 0.1 is probably recommended. I think the default is good. You can reduce it down to 0.05, or you could change that to a higher amount. I probably wouldn't do that. So that's the criterion. Now there's other criterion here, and these came in when Martin Bessener, our PhD, started up, I don't know how many years ago, it might have been 10 years by now. And he came in with one that the PhD statisticians like, and it actually is quite good. It's a goodness of fit criterion called the Ake criterion corrected. That's kind of a mouthful. But basically it's like a goodness of fit. And it's a little bit more versatile overall, especially let's say for happenstance data, if you're doing data mining or that type of thing. But what I find oftentimes, if it's not a big difference, if you go with something simpler that most people understand, it's probably better. And I've actually seen where p-values compete very nicely against AICC for design of experiments data. And sometimes p-values work better, but there's such a small difference in the DOE data that I think p-values is fine. And then there's some other criteria that you see here, but I won't talk about that. Now, the other thing that you have a choice on is something called the selection direction. And these algorithmic reductions are part of what's called a stepwise family. And you can either step backward from the full model and take out insignificant terms, or you can go step forward, starting with the mean and adding in most significant terms. And now you can see the alpha has shifted up, the field went up here. And then there's also a combination called stepwise, where it goes forward and then it reassesses and takes them out, going backward, and kind of goes back and forth. Now, honestly, I just find that if I go with the criteria of p-values backward and just stay with that, and I just use that all the time. So I would recommend that, but you can try some different things and see what difference it makes. And then we can start this and do, in this case, a backward elimination. And you can see that the AB did come out. We recognize that that was highly insignificant. A squared was another one, and then A came out. And it's a little bit mysterious, the order of this. Normally the p-value would keep going down as it's excluded until it gets to the 0.1, but because of the way it's refitting every time, it's dealing with some issues with the fact that these designs are not completely orthogonal. So I would just say, okay, fine, let's accept this, press ahead, and then say yes to hierarchy, and we end up with the same model. So nothing has really changed from the manual reduction. Okay, and then I'll just mention there's one other little cool trick that we can do with the newer versions of Design Expert and States 360 that I like, is if I have a question of the approach that I've taken, oftentimes I'll go back and rename this, just to recognize that I've done P back, okay, reduction. Okay, so now I've just done that. Now I'm going to go and say, start up a new line, and this one I'm going to say no reduction. And so if I had some concerns, or maybe this would be done using AICC forward or some other thing, and you can do as many of these little lines as you want. And so then I could just, in this one, just say, okay, never mind the model reduction. Some people argue with just a few factors. Norm Draper contacted me one time, one of the famous figures in response service methods, who worked with George Box, and he said, we don't really like the engineers reducing models so much because we don't know what they're going to do to it. And actually, he was right on for smaller models. Sometimes you're overdoing it. So you could just say, well, look, I'm just going to take the full model. And so now we have the full model here. And so we could then kind of toggle back and forth, and we could say, well, if we kept the full model, we would get a predicted R-squared of 0.7891. But if we reduce it, which seems like it was doing good, it actually caused the predicted R-squared to go down. However, there's some other attributes that we probably should focus on. We could look at the overall model F value, for example, but probably what I would focus on would be some things like the lack of fit and just seeing how that compares between them. And actually, I'm convincing myself that maybe I shouldn't have reduced this model, but I still feel like I would because I like having a smaller model. The adjusted R-squared, of course, we could go back and look at that. And so I'm just kind of going back and forth, and maybe we'd want to set up a little table separately to check on that. Now, there is one other stat that we have that I like a lot for model fit, and it's called adequate precision. Now, this adequate precision is explained in the blue part below in our software if you keep the annotations on. It measures the signal to noise ratio, and a ratio greater than 4 is desirable. And so in this case, it's quite good. And I use this as kind of a tiebreaker For example, oftentimes I see lack of fit is still present no matter what we try. But if all the other fit statistics are good, and particularly the adequate precision, I usually don't let the lack of fit be a showstopper, because all that really means is that when we did our replicate runs and measured the pure error, those are very close together. And I have a real suspicion of the high-powered scientists, let's say PhD organic chemists that I would work with, this was their standard condition around which they would vary the factors. And they were very good at running that center point. And so they would tend to get very small differences. But when they started getting away from that, the actual error, which is measured by residual, was much bigger. And so it would seem like, you know, the amount of difference you're getting from the points to the fitted surface is more than you would expect based on the pure error. But it could be that that pure error is underestimated. So lack of fit is something that I don't worry about as much, provided that this adequate precision is good. And just looking at the no reduction, again, you know, I'm building a case for not reducing this, but remember, we're not losing a whole lot by eliminating some of these terms. And so it does simplify things a little bit, and maybe it would be more helpful to explain what happened, you know, not to have the A squared, you know, or the AB term in here. That would be up to you. And like George Box said, all models are wrong, but some are useful. You have to be the judge of that. So we pretty much looked at the main things, you know, just trying to keep it as simple as possible that I would focus on for developing a useful model. However, before we start looking at the model graphs, it's really important to look at the diagnostics. And I mentioned that there's three that I like in particular. In terms of just the first look at it, we can always dig down and look at more diagnostics, but I would look at the normal plot of residuals. And you can't see me doing this at this point, but I'm taking my pen for my pen tablet and I'm putting it over this graph on the left-hand side, and I'm trying to see if the points are covered up by my pen for my pen tablet, and they are. So if this plot on the left, if the points line up, and we call that the pencil test, and I sometimes refer to it as a fat pen test because I've got a really fat pen. If any of you have taken training from me, you'll see me take it out of my drawer back at my other home up in Minnesota. I'm down in my second home in Florida right now, and I don't have a fat pen here. I'll have to go get one. But the idea of it is that don't overinterpret the normal plot. You're really looking for something that's really dramatic, like a huge S shape, or one point that's way off. Now the other one I like is this one here, and I'll maybe make this bigger, residual versus run. Because as a certified quality engineer, this was the type of thing I was always starting with before I ran a designed experiment. I wanted to make sure that the plant process was in control. So I would have them do a run chart, and then I would superimpose red lines at plus or minus 2 or 3 standard deviations. And usually in manufacturing, these points are actually subgroups of 4 or 5. But in this case, they're the individual runs, and we've measured the deviation using a specialized scale called externally studentized scale, which is like a normalized scale. It also is set up in a way that is resistant to having outliers that are kind of polluting the data, and that's called externally studentized. Again, you can look within the help system to learn more about these stats. But suffice it to say that we have a nice visual now, and we can see that there's no points out of the red lines. That indicates that we don't really have a lot of concern about any outliers with some special cause, that like the beaker fell down on the floor and broke up and the reaction was quenched, would be an example of where an outlier might occur. But there's nothing outlying here, no trends up or down. I had issues with catalyst reactions where they would be poisoned over time, and I would see a gradual downturn on this graph. But this shows a nice pattern, you know, randomly up and down, no trends, no runs up or down or anything like that. Now the third plot that I like to look at is this Box-Cox plot. And Box was very active in the field of DOE, did a lot of great things. Now this plot is pretty cool because it looks at various transformations of the data, trying not only just all the data to the power of 1, which is no transformation, but refitting after squaring all the data, cubing it, taking the inverse and all that. And then a special point on this bottom line called lambda, which is the power that you're taking to, is 0. If we took everything to the power of 0, that would make all the numbers 1, but this actually is a placeholder for the natural log. Now it turns out there's a zone here that we can look at that's a confidence interval. And this confidence interval in this case is going from minus 0.85 to 3.64, which is off the right of the graph. We're in the zone now, so there's really no reason to make a transformation. And that's all that I really want to focus on here, is where it says recommended transformation. All right, and so now we're done with this fitting. And so now we're ready to just, start interpreting based on the contours and the 3D graph. And for example, we knew that we wanted to increase the conversion to the maximum level. And so we're looking for these hot spots up here. And what does the temperature do? Well, we didn't see a lot of effective temperature when we did the fitting. So it's good that we did the fitting and thought about that. But we can slide this bar around, and actually increasing the temperature because of the interaction with the catalyst in particular is giving us an increase. And so we probably want to go to that high temperature then, right? And then we'll get, the absolute peak. Now we'll come back at this with the multiple response optimization. However, before we get ahead of ourselves, we do also have to look at the activity. So now that we've got the hang of it, we're just going to do the fit summary. Oh, whoops. Now this is a little bit of a surprise. Because we designed the experiment to fit the quadratic. That's what the central composite does, but it's saying only the linear. That's kind of disappointing. So now we better dig in on the sequential model of sum of squares and see what happened. Okay, so we regressed out the mean first. We always do that. Took away the block impact. We always do that. And when we look at the linear terms on top of it, or the main effects of the 3 factors, it's very significant. But look what happens when we add the 2-factor interaction terms. There's no advantage. And the quadratic is no advantage. So why overfit with extra terms? So what we'll do is we'll go ahead with the linear model. We'll look at the p-values of it. Now, you notice that temperature, again, is not having an impact. We could take that out. I mean, it'd be easy enough just to double-click that off, right? Or it'd be kind of ridiculous, but if you feel like you want to run the high power of the software, you could do the p-value backward, and that would say, oh, that should be taken out. But I probably would consider leaving it in. I don't know, just because it's informative to people to know that activity really isn't affected by the temperature, you could leave it in. But look at these adjusted predicted R-squared and adequate precisions. They're very good. By the way, here's where we would see the block impact, and you would assess that. You can also see the mean square of the block relative to the residual and assess it that way. And you can also do graphing, and we could look at the impact of block there as well. So we could look at the impact of block on the activity, for example, and you could even color by design type, and we could see that the center points are fairly consistent from one day to the next for the activity. And let's look at the conversion. A little bit of a difference between the days on the conversion, so you might look into that. So lots of other little things, but focusing on our model selection, I would say definitely we don't want to go any further than the linear. Now, if at this point you're saying, well, look, Mark, we paid for the quadratic, and we're only getting linear, and not even all the terms in linear. So we want the quadratic. So, okay, fine. You could do the quadratic, which is the design model, and you could assess it, and you would see then, there's lots of very high p-values for the nonlinear terms. So there you go. Now you might say, well, what if we reduce that? Okay, fine. We can reduce this, and there's no harm in this. And guess what? It ends up with the same model. And this is characteristic of designed experiments, particularly factorial design and responsiveness methods, is you won't see, much differentiation occurring with the different models. It's almost orthogonal in the case of the central composite design. Now, if you get into mixture designs and you were doing an experiment on catalyst, reagent 1, reagent 2, the catalyst would be in a very narrow range. You'd be in your triangular graph, and you'd have a very narrow track, and you could have a lot of collinearity, and then you might see differences between the models. But remember, we've got this little plus key, and that allows you to try some different models. So if you really wanted to do the quadratic model, you know, you could do it. We could say, let's do the full quad, you know, just because we want to show the Downing-Thomases, you know, that you're going to get a lot of extra terms here if you do that. So now we've got, you know, the two models, the full quadratic and then the reduced one, and you could, you know, show people what happened. And then, of course, we're always going to check diagnostics. And the three that I'm focusing on are the normal plot, residual versus run, and box Cox, which again, it's kind of hard to see it, but if I make this big, I'll be able to control mouse wheel this a little bit bigger, and I can see there's no transformation. And now these model graphs are going to be kind of boring. They're just straight lines on the contour graph and a tilted plane on the 3D surface. And that's about it as far as the model fitting, but you know, you're not going to be very satisfied if you stop here. So what you want to do is say, for a multiple response optimization to get the most desirable combination, is let's at least try to get 80% on our conversion, ideally up to 100. And then for activity, now I forgot what the goal was. Let's go back here. 63 is our target. And we want this to be in the spec range of 60 to 66. And we should be able to do this. I should have gone back to the activity and just looked at, okay, are we between 60 and 66? And I would say, yes, there's a lot of results that are in that range. So I think this will work. Let's just see what happens. It's going to search out and give you the number one solution. And it says, well, if you set up around 47 minutes at 90 degrees and about 2.7 catalysts. Now it turns out the time the temperature is not as important, or maybe both, depending on where you're at. So you'd want to kind of explore some of your options here, depending on whether time is of the essence. You could go back and say, well, I really want to minimize the time also, and you could add more requirements on this. And now that we've got useful models, we can do this what if and try all kinds of things. Catalyst is quite expensive. We would rather have that minimized, all else equal, and so we could try it again. And we're still doing pretty good. We're getting a little off target on activity at this point, but we've now saved time and we've reduced the cost of the catalyst. And I'll stop there. So that's about as far as I want to go. I'll just ask for a show of hands at this point if you were able to follow along fairly well with what I was presenting. Good, excellent. And of course, we can always go back to the recording and just, you know, study that and kind of go back over some of the things, because I have so much in my head to try to explain and try to help you that it's hard for me to try to keep it as simple as I probably should. But anyways, our topic was focusing on model selection and try to develop a useful one. And one of the things that was a focus here was this algorithmic model reduction. And so this slide just, you know, kind of summarizes our options with the criterion, the AICC, and some others. And then the selection method. The program, when you get it, if you don't change, the defaults will be AICC forward, which is perfectly fine. And this was something that Martin set up, and rightly so, because overall that might be the best approach for any set of data. But I find, having worked for decades with design of experiments data, that the more traditional p-value backward works perfectly fine, and it's a little easier to explain to people. So that's what I like, but you can do what you want. I mean, that's what's cool about having our software. You can set these options and, you know, go whichever direction you like. So final tips for modeling is that I would always try reducing the design for model. You know, it's worth a try. And oftentimes this would require that you would override what the model was that was chosen by the STATI software, which is based on the best combination of sequential p-values, lack of fit results, and fit statistics. By the way, one indicator of model reduction is if the adjusted and predicted R squared vary by more than 0.2, oftentimes reducing the model will bring up that predicted R squared closer to the adjusted. And this is one of the few things that I ever discovered. And so I always like to mention that rule of thumb because I observed that and I mentioned it to my superior at Stats, Pat Whitcomb, our founding principal. And then we talked to Professor Kinley Lawrence at School of Statistics, who was our advisor at the time. And after I showed them what was happening, they agreed that that made sense. So that's a good rule of thumb if I do say so myself. Now, another thing I'm going to suggest is be careful not to get overly concerned about the fine points of the model selection, because you might get what I call paralysis by analysis. And that is you're just spending too much time worrying about little tiny fine points that really don't matter. So at some point, just press ahead. I do suggest that the lack of fit in particular not be a stopper for you. If that happens to be significant, go back and look at the repeat runs that were made and consider, whether whoever was doing that wasn't really good at doing that central condition or standard operating condition. And or they might have gotten biased in the results. They might have gotten back and done a second run and thought, well, that didn't agree as well as I thought it should have, and they would do it over. I've also seen, really bad behavior where they've said, I'm not going to keep doing that condition over again. I'm just going to write the same number down. Well, that's pretty easy to spot. Or they'll say, I'll just run it once and take, 3 samples. Or they'll take 1 sample and say, I'll just take 3 measurements. So you really want to make sure that the repeats that are done for the estimate of pure error are done properly in a random plan from start to finish, recharge reactor, run it out, collect the data, and so forth. But you be the judge in the end, is the model useful? Now, one last thing which is really important is don't be shy about getting a second opinion from our Staties consulting team. Show us the data. Email your software file to StatHelp, and this is available for licensed users. Now, if you do go and take a trial of the software, which I highly recommend if you haven't, then you're going to email the file to me, Mark at staties.com, and I'll be glad to help you. So we've reached the end of the hour. Hopefully I met the objectives here of how to achieve a statistically solid predictive model, showing by example with our little tutorial data, some tips on deploying the algorithmic model reduction to get the most parsimonious model, insights on the key statistics for assessing your model fit, and then a quick briefing on some of the diagnostics, the top 3 that I like, for normality, outlier identification, and the possible advantage of a transformation. So you tell me, was the mission accomplished? Now I'm looking for some applause at this point, which is coming in the form of the hands. Okay, Tim, Verena, Wolfgang, all the rest of you, thank you for that. I'm shamelessly asking, for approval, so I appreciate you playing along with that. And Ola Saigon, I don't know if I'm pronouncing your name right, but I appreciate your accolade. Fantastic presentation. Can we have the slide or video? Okay, so when you go to the 3wstaties.com, go to the webinars, you'll find this presentation in the list, and then click that, and then within a day or 2, you'll see a YouTube video posted, and the slides themselves will also be provided. So just to finish things off, if you're interested in learning more about model selection, I would recommend this book, which is the middle one of my trilogy, the Simplified Trilogy. The RSM Simplified would give you the most insights into things like model reduction and other aspects of fit statistics and stuff like that. Keeping in mind that mixture design for optimal formulation will use similar tools, and for a book about mixture design in general, Formulation Simplified, and if you're just at square one doing screening and characterization with 2-level designs, start with the DOE Simplified as #1 book. So it might go like this, 1, 2 between DOE and RSM if your process If your mixture, just go straight into the mixture design book and it'll cover, mixture screening and optimization. Also, if you want to know more about model fitting and model selection, there's modern DOE for process optimization, which is, I think, 5 half-day Zoom at a distance if it's a public. If it's a private, I think it's 2.5 days on site. But you can talk to our workshops team to learn more about that. If you're involved with formulations, then we have a specialized class in mixture design. And then for private classes, various specific classes like design of experiments for biotech. Now, more recently, they've come up with smaller classes. We call them the essentials that are shorter. And if time is of the essence, we've got 2 half-days of intense hands-on learning. Again, either ask workshops for information or go to our website to learn more about that. So again, thank you for attending. I've run out of time, so I don't really have the chance to stay on for chat, but do send me email if you have any questions. So have a great day wherever you're at, or have a great evening if you're in a different time zone, and good luck with you pressing ahead to make the most from every experiment. Regardless, whether you're using our software or not, I definitely am very positive about using design of experiments, multi-factor approaches, using empirical modeling and all that. If you're working with StatE software, all the better. And then I hope to hear from you, with your data files, or send them to the stathelp@states.com. Okay, so thanks again. So long. I'm signing off. Bye-bye.